Of all the metals, aluminum is the 13th element on the periodic table, and is also a post-transition metal. With aluminum being the most abundant metal naturally found on the planet, and the second most used metal globally behind iron, aluminum is largely used as an alloy and has been used in a number of products from power lines to spacecraft components to trains and personal vehicles. Aluminum plays a huge role in the manufacturing process for many companies and organizations. In today's video, we will be learning about the mining, extraction, refinement, and production of aluminum. Before we get into the mining of aluminum, let's talk about aluminum ore. Aluminum is the third most abundant element on Earth's surface. Only oxygen and silicon are more common. Earth's crust to a depth of 10 miles contains 8% aluminum. Aluminum has a strong tendency to combine with other common elements and so rarely occurs in nature in the metallic form. Its compounds, however, are an important constituent of virtually all common rock. It is found in clay, shale, slate, and granite. The most important is aluminum ore. An iron-containing rock consists of about 52% aluminum oxide was discovered in 1821 in southern France. The material was later named bauxite. Bauxite is best defined as aluminum ore of varying degrees of purities in which aluminum in the form of aluminum hydroxide or aluminum oxide is the largest single constituent. The impurities are largely iron oxide, silica, and titania. Bauxite has been found in all the world's continents except Antarctica. The richest deposits generally lie in areas that during formation were in tropical and subtropical climates, providing optimal conditions of heavy rainfall, consistent warm temperatures, and good drainage. Now, not all bauxites are economical for aluminum production. Only earth with aluminum oxide containing about 30% or more is considered practical. By far the greatest quantity of commercially exploited bauxite lies at or near the Earth's surface. Consequently, it is mined in open pits, requiring only a minimum removal of overburden. Bauxite beds are blasted loose and dug up with power shovels or drag lines, and the ore is transported by truck, rail, or conveyor belt to a processing plant where it is crushed for easier handling. Refining plants are located near mine sites if possible, since transportation is a major item in bauxite's cost. Approximately 90% of all bauxite mined is refined into alumina, which is ultimately smelted into aluminum. The remaining 10% is used in other applications such as abrasive refractories and proponents in the recovery of crude oil. Approximately 4 tons of high-grade bauxite yields 2 tons of alumina, from which 1 ton of aluminum is produced. The production of aluminum from bauxite is a two-step process, refining the bauxite to obtain alumina and smelting alumina to produce aluminum. Bauxite contains a number of impurities including iron oxide, silica, and titania. If these impurities are not removed during the refining, they will alloy with and contaminate the metal during the smelting process. The ore, therefore, must be treated to eliminate these impurities. Purified alumina usually contains 0.5 to 1% water, 0.3 to 0.5% soda, and less than 0.1% other oxides. The Bayer process, with various modifications, is the most widely used method for the production of alumina, and all aluminum is produced from alumina using the Hall-Héroult electrolytic process. The Bayer process involves 4 steps: digestion, clarification, precipitation, and calcination. In the first step, bauxite is grounded slurred with a solution of caustic soda, sodium hydroxide, and pumped into large pressure tanks called digesters, where the ore is subjected to steam, heat, and pressure. The sodium hydroxide reacts with the aluminous minerals of bauxite to form a saturated solution of sodium aluminate. Insoluble impurities called red mud remain in suspension and are separated in the clarification step. Following digestion, the mixture is passed through a series of pressure-reducing tanks called blow-off tanks, where the solution is flashed to atmospheric pressure. The steam generated in the flash is used to heat the caustic solution, returning to digestion. The next step in the process is to separate the insoluble red mud from the sodium aluminate solution. Core materials is removed in crude cyclones called sand traps. Finer residue is settled in raking thickeners with the addition of synthetic flocculants. And solids in the thickeners overflow are removed by cloth filters. These residues are then washed, combined, and discarded. The clarification solution is further cooled and heated in heat exchangers and enhance the degree of supersaturation of the dissolved alumina and pumped into tall silo-like precipitators. Sizable amounts of aluminum hydroxide crystals are added to the solution in the precipitators as seeding to hasten crystal separation. The seed crystals attract other crystals and form agglomerates. These are classified into larger product size materials and finer materials that is recycled as seeds. The product size agglomerates of aluminum hydroxide crystals are filtered, washed to remove entrained caustic or solution and calcined in stationary fluids, bed flashes calciners at temperatures exceeding 1,750 degrees Fahrenheit. Free water and water that is chemically combined are driven off, leaving commercially pure alumina or aluminum oxide, a dry, fine white powder similar to sugar in appearance and consistency. It is half aluminum and half oxygen by weight, bonded so firmly that neither chemical nor heat alone can separate them. Aluminum produced by the Bayer process is quite pure, containing only a few hundredths of 1% of iron and silicon. The major impurities, residual soda, is present at levels of 0.2 to 0.6%. In addition to being the primary raw material for producing metallic alumina itself is an important chemical. It is used widely in the chemical refractories, ceramics, and petroleum industries. Refining 4 tons of bauxite to yield about 2 tons of alumina. A typical alumina plant using the Bayer process can produce 4,000 tons of alumina per day. The cost of alumina can vary widely depending on the plant size and efficiency, on the labor cost of the overheads, and on the cost of bauxite. To get alumina to alumina, you have to use the Hall-Héroult process. Smelting of alumina into metallic aluminum takes place in a steel vault called a reduction pot. The bottom of the pot is lined with carbon, which acts as one electrode, a conductor of electric current of the system. The opposing electrodes consist of a set of carbon rods suspended above the pot. They are lowered into the electrode solution and held about 1.5 inches above the surface of the molten aluminum that accumulates on the floor of the pot. Reduction pots are arranged in rows consisting of 50 to 200 pots that are connected in a series to form an electric circuit. Each pot line can produce 66,000 to 110,000 tons of aluminum per year. A typical smelting plant consists of 2 or 3 pot lines. Within the reduction pot, aluminum crystals are dissolved in molten crystallite at a temperature of 1760 to 1780 degrees Fahrenheit to form an electrolyte solution that will conduct electricity from the carbon rods to the carbon line beds of the pot. A direct current 4 to 6 volts is passed through the solution. The resulting reaction breaks the bonds between the aluminum and oxide atoms in the alumina molecules. The oxygen that is released is attracted to the carbon rods where it is formed carbon dioxide. The freed aluminum atoms settle to the bottom of the pots as molten metal. The smelting process is a continuous one, with more alumina being added to the crystallite solution to replace the decomposed compound. A consistent electric current is maintained. Heat generated by the flow of electricity at the bottom of the electrode keeps the contents of the pot in a liquid state, but a crust tends to form atop the molten electrolyte. Periodically, the crust is broken to allow more alumina to be added for processing. The pure molten aluminum accumulates at the bottom of the pots and is siphoned off. The pots are operated 24 hours a day and 7 days a week. A crucible is moved down the pot line to collect 9,000 pounds of molten aluminum, which is 99.8% pure. The metal is transferred to a holding furnace and then casted, poured into molds as ingots. One common technique is to pour the molten aluminum into a long horizontal mold. As the metal moves through the mold, the exterior is cooled with water, causing the aluminum to solidify. The solid shaft emerges from the far end of the mold, where it is sawed at appropriate intervals to form ingots of desired length. Like the smelting process itself, this casting process is also continuous. The properties of aluminum is that it's a ductile silvery white metal, usually with a dull luster alloying to a surface film of aluminum oxide. Aluminum is lightweight, approximately 1/3 as much as an equal volume of copper or steel. It is corrosion resistant and is an excellent conductor of heat and electricity. It reflects both light and radiates heat, and is non-magnetic and does not readily absorb neutrons. It can be safely used with food and medicine and can be formed by all known metalworking processes. This concludes my video on aluminum. Thank you for watching, and here is the sources that I used to make this video. Thank you.